Hello my dears, how are you all? I welcome all of you in the first session of fourth semester. Let us today begin with first chapter. The title of the chapter is Electromagnetic Induction. My dears, before we go for understanding this chapter, there is a physical quantity which needs to be revised, because that physical quantity repeatedly will be mentioned in the discussion. So let me make you clear about that physical quantity. It is none but magnetic flux. What do you mean by magnetic flux? I am showing you. Look, to understand about magnetic flux, you just consider a uniform magnetic field. That uniform magnetic field, in the figure, it is shown by parallel field lines, and you can see perpendicular distance between each two consecutive lines is same. That is why we call it uniform magnetic field. Okay, we just show it by symbol vector capital B. Now in this magnetic field, we just consider a surface or a loop which is inclined this way. Now just to have the arrangement of that surface in the space, we just define one vector which is called area vector or surface vector. And you must have studied in third semester that area vector is drawn always perpendicular to the plane of the surface. Right now this surface is something like this. Surface is something like this. If surface is something like this, then a vector which is drawn perpendicular to it can be drawn this way. Correct? Now such a vector is called area vector. Fine. That area vector or surface vector we have shown by symbol vector capital A. You can see in the figure, here is vector A, here is vector B, and then this is the angle between them, let it be theta. Now in this case, you can see there are certain magnetic field lines which are passing through this area of this loop, and then if that number is more, we say magnetic flux is more. If that number of magnetic field lines passing through a given loop is less, we say magnetic flux is less. So magnetic flux indirectly gives you measure of how many number of magnetic field lines pass through a given surface or through a given loop. My dears, remember that number itself is not a magnetic flux, because number does not have any unit, but magnetic flux has the unit. So all that you can say is that magnetic flux gives you measure of number of magnetic field lines associated or passing through the given loop or given surface. Now how do we define it? I am showing you. Look, the magnetic flux is shown by symbol phi, and it is defined mathematically this way. It is nothing but a dot product between area vector and magnetic field. That is how we write it here, vector A dot vector B. Fine. Now in first semester you have studied that the expression of dot product can also be written this way, AB cos theta. Come on, A is what? Magnitude of area vector. B is what? Magnitude of magnetic field. And cos theta, where theta is angle between vector A and vector B. Come on, phi equals to AB cos theta, or you can say vector A dot vector B. And you know very well that dot product is always commutative. So instead of vector A dot vector B, I may write vector B dot vector A, no problem. Correct? Now tell me, how would you define magnetic flux? Magnetic flux linked with a given surface or linked with a given loop is nothing but dot product between area vector and magnetic field. Fine. Now here we have considered the loop which is flat. You can say it is a planar loop. Okay. But it is not necessary that whichever surface you may consider in the magnetic field must be plane, not necessary. It may be curved also, it may be having some irregular shape, no problem. Okay. Now in that case, How would you find out magnetic flux linked with that surface which is having irregular shape? For that, we have just defined magnetic flux this way. Phi equals to surface integration of magnetic field taken over that entire surface. So you can define magnetic flux in general like this. Magnetic flux linked with any surface is nothing but surface integration of magnetic field taken over that entire surface. Such an integration is called areal integration. That's why we have written here small a. Okay, fine. Now what about unit of magnetic flux? SI unit of magnetic flux is nothing but Weber, and symbol of Weber is capital W small b. Later on we will come across two more units, equivalent units of magnetic flux. Two more equivalent units are this, come on, Tesla into meter square and also volt into second. Tesla into meter square, that unit we will obtain from here only. Come on, unit of magnetic field everybody knows, it is Tesla. Unit of area is, come on, meter square. And two articles later, perhaps in the next episode, we will study about this unit. Come on, unit of magnetic flux is also, come on, volt into second. How it is volt into second, I'll show you next time. Okay, fine. So there are three units for magnetic flux. One is Weber, another is Tesla into meter square, and third one is volt into second. Okay. Now let us consider some special cases. Here is the uniform magnetic field, and I have chosen a planar loop just perpendicular to this uniform magnetic field. Fine. If the loop is like this, then area vector which is to be drawn perpendicular to the planar area should be drawn this way. Correct? If the loop is like this, come on, I should draw area vector this way. Correct? In a direction perpendicular to the plane of the loop. Fine. Now here, vector A and vector B, they both point in the same direction, and you know, angle between vectors in the same direction is theta equals to 0 degree. So just place theta equals to 0 degree over here, and when you write theta equals to 0 degree here, you know cos 0 is 1, and that's why phi will be equal to AB. Phi equals to AB. But when you write cos theta equal to 1, you are putting its maximum value. That's why I am putting here phi maximum. Okay, fine. Now let us consider another case in which plane of the loop is just parallel to the uniform magnetic field. Magnetic field is also this way, and plane of the loop is also in the same direction. So plane of the loop is very much parallel to uniform magnetic field. Fine. If plane is like this, then area vector you can draw this way. Correct? In the figure you can see this is area vector, this is magnetic field vector, and angle between them is 90 degree. When theta is 90 degree, you may write here theta equals to 90 degree, cos 90 degree is 0, and that's why phi will be equal to 0. 0 means minimum, that's why I am writing here phi minimum equals to 0. Okay? So please remember, whenever any planar loop is perpendicular to uniform magnetic field, at that time maximum magnetic flux passes through it, and that's why that maximum magnetic flux I have written here phi maximum, it is equal to A into B, and whenever plane of the loop is parallel to uniform magnetic field, at that time no magnetic flux passes through it, that's why phi minimum equals to 0. Okay? Now with this basic concept, now we proceed, we begin with the real content of the chapter. Come on. Very first article is about Faraday's experiments on electromagnetic induction. Faraday's experiments on electromagnetic induction. My dears, history says that it was not Mr. Michael Faraday who had thought over this problem first. Actually, it was none but Mr. Ampere. He had thought how to get EMF without connecting battery in a coil or in a circuit. But then, at that time in his experiments, he was using some stationary magnetic fields, and that is why he could not get any success. Later on, in the year 1831, Mr. Michael Faraday had performed a series of experiments. Very minutely he had observed this phenomena, and then he came to one conclusion, and that conclusion, what is it called? The name of that phenomenon is called electromagnetic induction. Now what is that actually? Let us see. Mr. Michael Faraday had performed many experiments, but out of those set of experiments, in our syllabus we have to study about only 3 experiments. Let us see one by one. Look, here is the experimental setup for the first experiment, in which we find here a ring made up of soft iron. A ring made up of soft iron. You know, soft iron has very high magnetic permeability, and because of very high permeability, what does it do? It simply has a very great attraction for magnetic field lines. Fine. Now on this ring, what we do? We just wind 2 coils on opposite sides. One coil over here, another coil over here. Out of these 2 coils which are wound on these 2 opposite sides, let us call one coil as primary coil, which I have shown in the figure by symbol capital P, and let us call another coil, say secondary coil, and we have shown it by symbol S, capital S. P for primary coil and S for secondary coil. Fine. Then after, this primary coil is connected with a battery and a key. Fine. And this secondary coil is connected across some sensitive galvanometer. Sensitive galvanometer is that through which even when small current passes through it, then also it will show you large deflection, and that too very promptly. The one whose response is very quick, very prompt, is said to be sensitive galvanometer. Fine. Now, at present you can see this key is open. If this key is open, naturally no current passes through this primary coil. Okay. But now, when we press the key and when these 2 points come in contact, at that time circuit is made closed, and so some current will pass through this primary coil. You have studied in 3rd semester that electric current is nothing but a source of magnetic field. Because there is a flow of electric current through the primary coil, it will produce its own magnetic field. But now, for that magnetic field, you can see its magnetic field lines prefer to pass through this soft iron ring because of its very high permeability. Surrounding medium might be air medium, might be vacuum, which has very low permeability, and compared to that, this soft iron material has got very high permeability. That's why magnetic field lines prefer to pass through this ring. Fine. And when they pass through this ring, and when they form closed loops, at that time they have to compulsorily pass through the secondary coil. So now through this secondary coil, certain magnetic field lines are passing, and you know, if more magnetic field lines are passing, we say magnetic flux is more. If less number is passing, we say magnetic flux is less. So I mean to say there is some magnetic flux associated with the secondary coil. Fine. Now, when this flux is associated, then also there was no deflection in the pointer of this galvanometer. Now tell me, though magnetic flux is linked, and then also here there is no deflection, meaning thereby there is no current passing through this secondary coil. And that is why this pointer is not showing you any deflection. It remains at the central 0 position. Fine. Now tell me, there is no deflection here, there is no current here. It means to say, to obtain current in the secondary coil, perhaps the magnetic flux is not required. That was the conclusion drawn by Faraday. Because if magnetic flux is required, then magnetic flux is already present, and then also there is no deflection here. It means to say, for obtaining current through the secondary coil, magnetic flux is not required. Just thinking on the same idea, Mr. Michael Faraday in the second experiment had simply removed the battery. So he had removed this battery, okay, and without battery he had performed another experiment. Let us see what was that. Come on, in the second experiment you can see there are two bar magnets which are arranged in a V shape, in a alphabet, English alphabet V shape. These two bar magnets are arranged, and between these two ends you can see there is a cylindrical rod made up of again soft iron having high permeability, on which there is a winding of thin isolated copper wire across which some sensitive galvanometer is connected. Fine. Now at present there are magnetic field lines passing through this cylindrical rod, because you know magnetic field lines, they just move from north to south pole, and when they approach from north to south pole this way, those lines are passing through this coil, okay. In short, this coil has some magnetic flux. Fine. Though this coil has some magnetic flux, there is no deflection shown by this pointer. Then after what Mr. Michael Faraday had done, he had simply moved this upper magnet this way, up and down this way. And when he had moved upper magnet up and down this way, at that time he had noticed very carefully, very minutely, that here this pointer was showing the deflection. During the downward motion of the upper magnet, naturally, because it is coming closer, more magnetic field lines will pass, more magnetic flux will pass. So because of increase of magnetic flux, at that time he got, say, deflection towards right hand side. Then while withdrawing the magnet away, that is on upper side when it was moved this way, at that time because of decrease in magnetic flux, this pointer had shown the deflection on the opposite side. I mean to say, for as much time the upper magnet was continuously moved up and down, for that much time this pointer had shown the deflection right, left, like that, okay. Fine. Then in the third experiment, Mr. Faraday had arranged two coils in the horizontal plane. I mean to say they are parallel to each other. One is primary coil across which battery is connected. Another is secondary coil across which sensitive galvanometer is connected. Fine. Now tell me, here through this primary coil, because of the battery, some current is passing. Correct? Fine. Now this current will produce its own magnetic field. You know from third semester, through a circular ring, if current is passing this way, then you can just think of the direction of magnetic field. How? I am showing you. Just hold the axis of that circular ring in the right hand palm such that finger should be given turn in the direction of current this way. And then direction shown by the thumb, which is right now vertically downwards, will give you direction of magnetic field. That is why these magnetic field lines are shown this way, which indicate downward magnetic field. Fine. And now because of this magnetic field, you can see these magnetic field lines pass through this secondary coil. I mean to say it now gets some magnetic flux. Okay. Though there is a magnetic flux linked with the secondary coil, this galvanometer had not shown any deflection. But then after what Faraday had done, keeping upper coil at rest, he had simply rotated the downward coil this way. The lower coil he had rotated this way, and during the rotation, you can see, this is the coil, and if I am going to rotate it this way, naturally the angle between vector A and vector B will change. If angle between vector and vector B keeps on changing, you know from this formula, if theta is continuously changing, then magnetic flux also will change. And at that time, if magnetic flux is increasing, then this galvanometer was showing the deflection on one side, and if magnetic flux was decreasing, this galvanometer had shown deflection on opposite side. Fine. Not necessary that you have to rotate only secondary coil, not necessary. Keeping lower coil at rest, you may rotate upper coil also. At that time also, this galvanometer shows the deflection. Now tell me, out of this all experiments, what is the common conclusion? Common conclusion is that through whichever way, in whichever manner, if there is a change in the magnetic flux linked with any coil or any circuit, then what happens? There is some EMF which is developed, generated across the two ends of that coil. That generated EMF is given specific name, and that specific name is induced EMF. What is it called? Induced EMF. And if that induced EMF is developed in a closed circuit, it will cause some flow of electric current also, and that current is known as induced current. And this whole phenomenon, in which without connecting battery, just by the change of magnetic flux, we are producing such a current, is known as electromagnetic induction, invented by Mr. Michael Faraday. Then let us define now what is called induced EMF, what is called induced current, and what is called electromagnetic induction. Let us define all the three terms together. Whenever there is a change in the magnetic flux linked with any coil, then across the two ends of that coil some EMF is developed, which is called an induced EMF, and any current caused by that EMF in a closed circuit is called induced current, and this whole phenomenon is called electromagnetic induction. I repeat, whenever there is a change in the magnetic flux linked with any coil, then some EMF is developed across the two ends of that coil, which causes some current to flow in a closed path. Such an EMF is called induced EMF, such a current is called induced current, and this whole phenomenon is called an electromagnetic induction. Fine. Because of this invention made by Faraday, there was a dream of mankind how to convert this mechanical energy into electrical energy. That dream was realized. So ultimately mankind got a great benefit after this invention. Now let us go for second article, which is also very interesting. It is about Lenz Law. But before we go for Lenz Law, I would like to discuss some few points which you have already studied in third semester. Just let me remind. Look, suppose we have, say, solenoid in which winding is made over some soft iron isolated cylinder. Fine. Now when we press this key, correct, naturally current will flow from positive to negative. Fine. Now before pressing the key, you know what we have done? We have placed here some magnetic needle in which this red colored part is north pole and this blue colored part is a south pole. Fine. So this is the initial situation of the magnetic needle. Now what I do, I just press this key. Okay, fine. Then I know that current is going to pass from positive to negative. Right, this way. Now this direction of current, if I observe from this end, this way. If I observe from this end, then direction of current I will find it this way. This way. This way means what? This way means what? Anti-clockwise. To me, I will find it anti-clockwise. Had it been this way, then clockwise. Because it is right now this way, then anti-clockwise. Fine. Now that current is passing anti-clockwise, correct? Now tell me, this current will produce its own magnetic field. Now in that magnetic field, it so happens that this end starts behaving like a north pole, and that is why this north pole is getting repelled, because you know like poles always repel each other. So after repulsion, what happens? This magnetic needle just undergoes a rotation of 180 degree, and finally it is getting settled in this position. It means to say, when you pass current through this end in the solenoid this way, that is in anti-clockwise direction, then that end behaves like a north pole. Then only it will repel this north pole. Okay. So just to remember, I have drawn this figure here. In any case, if you find direction of current say anti-clockwise, then that particular end of that coil will behave like north pole. That is why I am putting here letter capital N, and just at the two ends I am putting these arrows, and if you join these two arrows you will get, come on, letter capital N is there, and if you join these two arrows you will get the direction which is anti-clockwise. Okay, fine. Now tell me, here instead of having winding this way, suppose you are having winding this way, correct? Or in the same situation, if you revert the terminus of battery, then through this end, when you observe, current will not be passing this way, it would be passing this way. And when you observe from this side, if a current is passing this way means what? Clockwise. At that time, that end of the coil behaves like south pole, for which I have written letter capital S, and at the two ends if you place arrows, and if you join these two arrows, you will get the direction which is nothing but clockwise direction. Please try to remember both. If not, then at least one thing you must remember: anti-clockwise direction means north pole. Anti-clockwise direction means north pole. Let us summarize these two results. Whenever we observe perpendicular to the cross section of current carrying coil from one end, and if we find direction of current say anti-clockwise, then remember that end which is facing the observer behaves like north pole, and if the direction of current is found to be say clockwise, then that end of the coil facing observer behaves like south pole. Okay. Now after clearing this idea, let us go for discussing about Lenz law. Look, here we have some coil, correct, connected with sensitive galvanometer. In short, this is a closed circuit. Fine. Now we have some bar magnet here. Say this is north pole, this is south pole. You know, bar magnet has its own magnetic field, and just to have pictorial presentation of magnetic field, what we draw in the figure, we draw magnetic field lines. That is why I have shown some of the magnetic field lines. Fine. Now out of this many magnetic field lines, you can see there are certain field lines which are passing through this considered coil. Fine. And because of that number, you can say there is some magnetic flux associated with this coil. Fine. Now what I do, I just move this magnet towards this coil. If you move this magnet this way towards the coil, you know what happens? Because of the motion of magnet towards the coil, the distance between coil and the magnet goes on decreasing. And because distance is decreasing, more and more magnetic field lines pass through this coil. That is why you can say magnetic flux is increasing. And during that increase in the magnetic flux, you know what happens? There is a flow of electric current in the coil this way, and deflection is shown in the galvanometer towards the right hand side. And if you observe the direction of current through this end, say facing this bar magnet, through this end when you observe, you will find it this way. This way means what? Anti-clockwise. Fine. There lies the objection raised by Mr. Lenz. What did he think? He thought that let this magnet move closer, no problem. Let magnetic flux of this coil increase, no problem. Let some EMF be induced across the two ends of this coil, no problem. Let it send some current through this coil, no problem. The problem lies why the direction is anti-clockwise when you observe from this end. Why not clockwise? Why not clockwise, and why here only anti-clockwise? That was the point of interest from Mr. Lenz, and just to satisfy his query, he had performed a series of experiments and he came to one conclusion, and that conclusion is known as Lenz law. Just to satisfy his query, he had performed a set of experiments. He came to one conclusion. This conclusion is known as Lenz law. I am showing you what is that Lenz law. Look, here is a statement of that Lenz law. Direction of induced EMF and induced current are always such that they can oppose very cause producing it. I repeat, direction of induced EMF and induced current are always such that they can oppose the very cause producing it. Let us try to understand this whole statement slowly. Look, what is the root cause for the production of this induced current? Then that root cause is not this magnet but its motion. See, magnet is not responsible for this current. If the magnet is at rest, then there will be magnetic flux, but there won't be any change in magnetic flux, no change of flux, then no induced EMF, no induced current. Here you are getting induced current because of not magnet but because of its motion. Now according to Lenz law, tell me, direction of induced EMF and induced current are always such that they can oppose very cause producing it. What is the cause for the production of this induced current? Cause is the motion of the magnet. And if the motion of that magnet is to be opposed, then you may say that this face of this current carrying coil facing bar magnet should behave like north pole. Then only it can repel the north pole of approaching magnet. Fine. But now you know, if this face of this current carrying coil has to behave like a north pole, then direction of electric current when you observe from this end, then that direction of electric current should be come on anti-clockwise. And that is why the direction is anti-clockwise. So Mr. Lenz wanted to know why this direction in this case is anti-clockwise. That is what he had explained very nicely. But in this whole explanation, you have taken granted that Lenz law is correct. But now we are not going to take it granted. We will prove that Lenz law is correct. Let us prove Lenz law using law of conservation of energy. Look, what does law of conservation of energy tell you in very short, very simple words? Look, law of conservation of energy. Law of conservation of energy. It tells you that energy cannot be produced without spending energy. No energy can be produced without spending energy, correct? Come on, law of conservation of energy. This law tells you that you cannot produce energy without spending energy. Okay, fine. Now using this law, we are going to prove Lenz law. How? I am showing you. Just do one thing. Just assume. Let us adopt method of contradiction. In the method of contradiction, what we have to do? The correct result, the result opposite to correct result is to be assumed. Here, Mr. Lenz says that this face of this current carrying coil behaves like a north pole. Okay? Mr. Lenz says that this face behaves like a north pole. But we are not ready to believe. Then what we will assume that in this case, in this condition, suppose this end, this face does not behave like a north pole, but suppose it behaves like a south pole. Fine. Then tell me, just push this magnet very little, okay? When you push it very little, then it will go very slightly towards the coil. And because of that, magnetic flux of this coil will increase but very slightly. And because of that, you will have very slight production of induced EMF, and that is, then after very slight amount of induced current will flow. But if this phase has to behave like a south pole, then you know direction of current should be clockwise. That is why here through this coil current will flow clockwise. According to our assumption that current has to flow clockwise. If current is flowing clockwise, then this phase will start behaving like a south pole. Once this phase starts behaving like a south pole, you need not to push this magnet. Don't do any work. Don't spend any energy. You simply wait and watch. You know this south pole will attract this north pole because unlike poles attract each other. Unlike poles attract each other. Fine. Because of that attraction, what will happen? This magnet will have some acceleration towards this coil. So gradually the magnet will be speeded up towards the coil, and suppose that accelerated motion of the magnet towards the coil continues for T time. Then you know from third semester, if I amount of current passes through R resistance for T time, then amount of joules heat produced in that resistance will be equal to H equals to I square RT. Fine. Now tell me, here we have not done anything. We have not done any work. We have not spent any energy, and yet you are having production of such amount of heat energy. Now tell me, is it possible? No. Had it been possible, then it would violate the law of conservation of energy. But let me tell you, law of conservation of energy holds good. It is not getting violated here. Your assumption is wrong. Then in this case, this phase cannot behave like a south pole. If it does not behave like a south pole, meaning thereby it has to behave like a north pole. And then the same thing was told to you by Lenz Law, that this phase behaves like a north pole, and same thing is told by law of conservation of energy also. So I mean to say, Lenz Law is nothing but an equivalent statement of law of conservation of energy. Whatever is predicted by Lenz Law, same thing is predicted by law of conservation of energy also. So I mean to say, Lenz Law is nothing but an equivalent statement of law of conservation of energy. Fine. Now tell me, if this phase is behaving like a north pole, and then also you want to push this north pole closer to the coil, then naturally you will have to do work against the repulsive force provided by this north pole. And when you do that work, you have to spend energy. When you spend energy, then at the cost of that energy spent by you, will be having production of this much amount of heat energy. So at that time, we are spending energy and we are getting production of this much amount of heat energy. So law of conservation of energy holds good. It is not getting violated. Okay, fine. My dears, let us do little practice. Look here. If you push this north pole towards the coil, then remember, because of Lenz Law, we can say that this face of the coil facing this magnet will behave like a north pole. Then only it will oppose the motion of this north pole. Fine. But in the same condition, if this magnet is moved, look here, this way. This way means what? This way means what? Away from this coil. Then at that time, remember, this phase will start behaving like a south pole, such that it will attract this north pole, and thereby it will oppose the motion of this magnet away from the coil. Now consider other two possibilities. Suppose we revert the magnet. If we revert the magnet, then instead of north pole, what we will expect here? South pole. And if that south pole is moved towards the coil, then this phase will start being like a south pole. And if that south pole is withdrawn away from the coil, then this phase will start being like a north pole. Direction of current through the coil will be always in such a direction such that the motion of the magnet is getting opposed. If magnet is trying to come closer to the coil, then it will not allow that magnet to come closer. And if the magnet is trying to move away from the coil, then also coil will oppose its motion, will not allow that magnet so very easily to move away from the coil. I repeat, remember, because of Lenz Law, you know what will happen? If this magnet is moved closer to the coil, then also its motion will be opposed, and if this magnet is withdrawn away from the coil, then also its motion will be opposed. And not necessary that you should keep this coil at rest and you should move only magnet. Not necessary. You may keep this magnet at rest and you may move this only coil. Then also this thing happens. I mean to say, because of Lenz Law, you know what happens? The relative motion between the coil and the bar magnet is getting opposed. Fine. I repeat this statement of Lenz Law. The direction of induced EMF and induced current are always such that they can oppose the very cause producing it.